Somebody always have this part of public policy.
Okay, I think we're ready.
You're so nervous, right?
So it is my pleasure to introduce Professor Wolfgang Kerzendorf. He did his PhD at the Australian National University with Brian Schmidt on type Ia progenitors, and did postdocs at Toronto and an ESO fellowship before coming here to join us at NYU for a year, and is now a professor at Michigan State University. He's an expert on radiative transfer and failing to find surviving companions for supernovae. And yeah, he's going to tell us today about his research group's work on radiative transfer and supernova modeling and the machine learning and statistics tools that they use.
And he's Mark's
And he's also my co-advisor.
a very important part of the CV.
Thank you very much for the wonderful introduction. And I'm just gonna try to get rid of this so we can see the flow. Is there a way to
Click the
minimize?
yeah.
Yeah.
And you can move that off.
Good. Thank you very much for the invite. It's a pleasure to be here. As several of you might still know me, I was here for a year and I was Mariam's senior research associate because postdoc wasn't available, and so I didn't get postdoc housing. I'm still a bit in Twister, right? So it was a wonderful year. And it's very nice to be back, and it's very nice to see you all again. And obviously, I'm going to start with the wonderful 1A supernova 94D, the first supernova that was observed with HST. And I think it's sort of like a reminder of why supernovae are so special. They can outshine entire galaxies during their peak brightness, which I think is great. So I'm going to talk today about demystifying type Ia supernova, which is not too dissimilar to my thesis title, which was type Ia supernova explosions progenitors. That means, like, despite many years of funding, I still have failed to finish my thesis. And I mean, no, it continues. I've now dragged other people into this. And so, just to give you a quick overview of what happened after NYU, I went to MSU. I'm now assistant professor there. Started 6 months before the pandemic, which was great, the first 6 months, and then it started to suck. I'm Michigan State University. I'm between physics and astronomy in a new department called computational mathematics, science and engineering. And here I do astrophysics, and I do partially astrophysics. 70% astrophysics is my contract, and 30% data science. I do care a little bit more about life and death of stars, and also think about research infrastructure. How do we work together? And I'll see if I get to that point. We'll see how many questions there are. And I really hope there will be many questions, because I think I love to hear myself talk, but I love dialogue more. So please do step in. So I work on supernova remnants, surviving companions, or failing to find surviving companions, as Mark put it. I work on stellar populations around supernova remnants. I work also on the nuclear star cluster, specifically on the origins, like stars at extreme metallicities near the nuclear star cluster. And obviously you can test GR as has been done by several groups in the US and in Germany and other places. And I do stellar parameter inference. I think that's where we have a joint hobby, David and I, so to speak, on that front. Transients, I like to do reverse engineering of the explosions. I'm the PR of the TARDIS collaboration, and I like linking data to modeling with machine learning. And so, last but not least, I like to do AI, this AI research assistant. I'm potentially talking about more about this, but please do ask questions afterwards if you're interested in this. So let's go back to demystifying type Ia supernovae. And we're trying to do this with a little bit help of this lovely gentleman over there. And obviously, this doesn't work by itself, but you need to work with people from other fields, people that can give you advice and can sort of guide you. And so a lot of the work that I'm going to present today is not my work. It is work by people in the TARDIS collaboration, several individuals I'm going to highlight, but I want to make sure that it's clear that even they're embedded in a wider collaboration that includes many different people. And on this note, I'm going to introduce the team here. That's Andrew Fuller, Sona Chichian, and Jack O'Brien at MSU. And Mark Williams is another person that you know, and these are all astrophysicists. But we also have people that are on the computer scientist side, as well as on the software engineering side. And then we have one lonely astrostatistician. And I'm obviously happy for anyone to join the collaboration, who's Johannes Buchner, who some of you might know through his multi-nest Python bindings, which a lot of people use. We have a few summer projects, and I'm gonna quickly sort of highlight this. We're an interdisciplinary open science collaboration, and so please, if you have interested student, we have a Twitter handle for now. You don't need to be an expert coder and just interested in working on team and learning. So I think I really want to highlight this because we're getting into the summer. There's some students that are looking for interesting projects. I just thought this is a good place to highlight this. Okay, so now onto the real science. Now that we got the logistics out of the way, why should I care about type 1a supernova? In this case, it's you care about type 1 supernova. And there's three sort of rungs that I want to discuss. Obviously, the first one is they're reliable distance indicators, and they let us measure the expansion history of the universe, and then let us measure the equation of state of the universe, and let us discover dark energy. And so this is one of the things, the better we understand them. For now, this is only an empirical calibration. All the type 1a supernova measurements, cosmology measurements, we're using empirical calibration. There's no physics in it. It's pure empirical calibration. We care about them from a nucleosynthesis point of view because they make the majority of the iron, and this is a wonderful plot by Chiaki Kobayashi. And we can see the red parts here is the iron, and so they do have an influence on planet formation, but also life, specifically for us, from an oxygen point of view. And I think they're also interesting endpoints of stellar evolution. I think they really are an interesting way to sort of make stars explode, and I think that's another reason why you should care about them. So the question is, what makes a type 1a supernova? And there's two indicators. First one is they do not show hydrogen. There are a few things in the universe do not show hydrogen. It's one of them. Second one is they seemingly are powered by the radiative decay of nickel 56 and cobalt 56. So if you plug on if you plug the numbers of 6.6 days, I think, and 77 days for cobalt 56, and do a diffusion calculation, you will get a light curve that looks very, very similar to this. So essentially, what we know, it must be the nuclear burning in degenerate CO matter, and it must be something white dwarfs. So the question is,
by the way, are those arguments about fake nickel 56 and cobalt 56, are those purely timing in the sense that the light curve is very well fit by the two half-lives?
Yes.
Or is it also, is there also spectral confirmation that those are what are powering it?
There
or is it really
now,
fundamentally
there's multiple aspects. One of them is spectral confirmation through gamma rays. So we have for one type 1a supernova, we have early gamma ray observations. So this is 2014J. They make,
and that's what, new star?
that is no integral.
Integral.
And that is one of the informations. In the spectra, they have copious amounts of intermediate mass elements. They don't, in the early days, they don't have that much iron group elements. And so most of the iron group elements are actually produced in the center, which we do see in the end in the nebular spectroscopy. So we do see the iron in the nickel 56 make.
But this fundamental argument is a timing.
This fundamental argument is an energy as well as a timing. You need to sort of also sorry,
Yeah, the other thing was, I think from very early data light curves, you can get a radius, and the radius was small. So
yes.
Something like a red dwarf.
Yes. So one of the 2011 FE, I think they could detect this very early on and could say from a pure R squared t to the fourth argument, it must be very, very small.
Very small, right? Good.
So one of the things that I want to say is type 1a is an observational classification. It shows silicon and no hydrogen. But there's many supernovae of different sort of spectral look or look and feel that are type 1a. And I want to make clear this is here absolute magnitude versus a measure of drop in magnitude after 15 days from peak in a certain filter. How quickly does it drop off? And these are all supernovae on there that show strong silicon and no hydrogen. And they cover 2 orders of this is real this is not funny units, but this is real magnitudes. So 2 orders of magnitudes in brightness. The ones that we use for cosmology are only a small fraction of those. But in theory, these are potentially, all of these are exploding white dwarfs. And so explaining all of them will probably help us to sort of explain subgroups as well. And I'm going to focus today on the one that we use for cosmology, but we're working on more than this. And so the ultimate question that you will ask me is like, okay, white dwarfs should not ignite. What the hell? I mean, they should just cool for eternity. And so what happens? And I mean, as I did my poster with Mark McCurk, he put it in a really nice way. He sort of said, like, how about, like, we put density on the x-axis and temperature on the y-axis, and then we have a line where we say this is where the neutrino cooling timescale equals the carbon-carbon burning timescale. And so the question is, or what we have to do is bring the star from here to here. Right? And so this is like this is the question that has plagued the Type Ia supernova group for, I don't know, the last 20 years. How do you do this? And essentially, one of them is like, if you do slow accretion, and you can essentially get the center of the star near 10 to the 9 grams per cubic centimeter, it auto ignites and you have a runaway explosion. And this is the typical traditional scenario that we've all seen in textbooks. There's a second scenario where you essentially accrete helium, and then you have helium shock waves, so you have helium burning around the star, sending shock waves into the center.
Meaning the helium accretes on
The
and
helium
then
accretes
burns
onto the
up
white
to-
dwarf, then it burns and sends shock waves into the center, compressing the center, and then at some stage you can see like kaboom. This is super cool, I think. This is one of my favorite scenarios because it looks so cool.
So yeah, I mean, remember, slow accretion is for hydrogen, and hydrogen has a lower temperature, that's why it's kind of on that side.
Yeah.
This helium burning needs higher, and so it's higher on that.
Yeah, I mean, and the helium burning is
Fusion.
also much quicker. And then the last one is like, you can have a spiralin, and these are two white dwarfs, not to be confused with neutron stars. And during that spiralin, you have a temperature. You essentially create hotspots, and then you're relatively low density but at high temperature, and then makes the runaway. And so why do we care? Because all of these have different evolution times, different nucleosynthesis, and different luminosities. So we understand those better. They will help us with all three pillars that I mentioned before. One of the pet peeves is like, we run around and start and say like, there's Chandrasekhar mass explosions. There are no Chandrasekhar mass Type Ia supernova. So like, let me go into this. They're all near Chandrasekhar mass. So essentially, like, as we go to the Chandrasekhar mass, like Chandrasekhar introduced this nice idea that if you have relativistic electrons in there, your radius goes to zero. It goes really to zero in the solution. So if you turn this around and you density versus mass, essentially at some stage you cross this threshold. Not at the Chandrasekhar mass, but near the Chandrasekhar mass. Okay, so we have now three different scenarios. What predictions do they make? One of them, as Mark alluded to, is surviving donuts. So essentially, in both of these cases, here on the right-hand side, you have for the converging shock waves and for the other star, you will have a surviving companion. And this is a very nice simulation from Rüdiger Packmann et al. 2008, which sort of shows what happens, and I'm hoping this plays well, what happens with a companion star when you sort of hit it with a 1A shock wave. And you can see it's not disrupted. I mean, the shock wave runs through the star and heats up the interior of the star, but it's not disrupted, and essentially it will remain and should be visible. So this has been the bane of my existence, and for many supernova, in Tycho, we sort of myself and other groups looked at this and sort of didn't find anything. The same is true for 1006, which is another remnant. The same is true for Kepler, which is another remnant. And so the question is does this mean these companions don't exist? So we always look to roughly a solar luminosity, because I mean, ultimately when you hit a star, it should be brighter than a solar luminosity. But now with these helium accretions, you often have helium white dwarfs, which are the donors. And so that means potentially you have helium white dwarfs left over. And so what Ken Shen and a couple of other people did, including myself, is we looked for really fast flying, we are looking for really fast flying helium white dwarfs originally. And what we found in Gaia in 2018 were these fast flying things that are not quite white dwarfs, but they're essentially somewhere in the middle between main sequence and white dwarf. Maybe puffy white dwarfs, we're not sure. And so people were then saying like, okay, maybe like, no, it is not a normal main sequence star that donates mass, but it's one of these white dwarfs. And there's very few remnants where you can look for faint blue things, because most of the remnants are on the disk, because ultimately, like, most of the remnants are where the stars are.
Just one sec. So,
Go ahead.
so when you said the white dwarfs, you said it's fast white dwarfs. Do you have any other indication that they're white dwarfs besides?
They have like
color?
they have like
Spectrum?
spectral.
Okay.
They're spectrally confirmed. I mean, they're unusual spectra. It's still being studied. They're unusual objects.
Because the stellar remnants, if it was a normal main sequence star, it would have weird photosphere, right? Predominantly, I mean, if you got hit by, just heated up, got hit by a shock wave, perhaps there's pollution,
So
elements, so
yeah.
it should look not like a normal main
So
sequence.
essentially, I think there's multiple interesting points there. So probably there's relatively little pollution, because like anything that sort of falls onto the star is potentially like by convection, like added into the star, and so it's not that much. A lot of the stuff that will be in the supernova shockwave is very hot, so will evaporate off. And so main sequences are surprisingly compact. So when you hit them with a supernova shockwave, they don't change much. Like they puff up a little bit. What really is striking, if you hit a red giant, it sort of strips away the envelope. But for main sequence stars, they're like really like stocky little stars that like can take a beating.
When you found these fast-moving white dwarfs, were you looking for kinematics that relate to existing supernova remnants, or is this just in general fast-moving?
No, we were in general looking for fast-moving stars, and then moving them like
they
thousands.
might be the outcomes of some violent astrophysical.
And so we were saying like, there should have been 30. We found 3. And so one of them points back 100,000 years ago to a remnant.
That's good.
Some authors of this paper, I'm one of the authors of this paper, some authors of this paper sort of say like, oh, that clearly shows that this comes from this remnant. But I think if you point any star throughout the disk, you're going to hit a supernova remnant at some stage. So I would say, I don't know. I wouldn't bet a lot on this.
Got it.
Go ahead.
How fast are you classifying?
I think 2,000 kilometers per second, something like that.
So seriously unbound. They will
Seriously
be-
unbound.
Yeah, that's very fast. Usually it's like 30, 50.
No, like seriously fast.
So-
Because they're so close during the accretion process.
Good.
So you mentioned as an aside that if you would strip the envelope off of a red giant.
Yeah,
and then can you look for that thing? It's
So that
Yeah,
probably
would
becomes
it look like that?
No. This would much brighter, like
Would
10
it-
to the 5 solar luminosities or something like this. There's a paper of Marietta et al. 2000 that sort of looked at this, and like for a long time they will be very, very bright, like Vega or even much brighter than Vega.
I see.
So we think that if these are 1A remnants, they come from this like white dwarf accreting onto the other white dwarf. So one of the hypotheses, I love hypotheses and testing hypotheses. People that work with me don't know that. So one of the hypotheses that does this is like, if these are the outcomes of 1A supernova, then we should be able to go to a remnant and say, we should want to find one of these stars. But the problem is like, they're relatively faint and blue, and like looking in the disk is not easy to do. So essentially, there's one type 1A remnant called 1006, which is above the plane. You can see like, it's not in the plane, but it's above the plane. And so this is where like, Josh, one of my grad students, started to look. So classic accretion scenarios already ruled out for galactic remnants. So we went for this weird one. And so we're searching for white dwarf companions as suggested by the double detonation scenario. It's difficult, as I mentioned. And 1006 is the only young 1A remnant significantly off the disk with minimal reddening. And so we did decap astrometry plus Gaia astrometry to sort of like, do a search for something faint and fast. And essentially this is what you found. Like, this is where these companions are, and we did not find anything down to this limit. So in 1006, we did not find a Shenandoah 2018 star. So that means like, whatever these stars are, some type 1A supernovae don't make them. There's stronger claims you can make, and you can say this scenario is wrong, but we can say, at least for 1006, there's no such star in there.
And you know that 1006 is a 1A?
Yes.
What if it moved away from us? I mean, it would be very unlikely that it's like literally moving
No,
away from
oh, I
us.
see.
And so it
Oh,
would be,
from the
you know,
promotion.
1,000 years,
Yes,
right? Like
yes.
1,000 years. It would
Josh
follow.
has done the calculations, and I think it's like less than 1% or something like this. I mean, yeah, it's a very good question. And we thought about this, and we'll just send you the paper. I mean, I know it's in there. Yeah, I mean, it's unlikely. It could still be, yes, you're right.
And 1006 did go off in 1006.
Yes.
Is that accurate?
Was observed in Europe mostly by a monastery in Switzerland, because they had their act together. The Italians and like the Europeans, the Southern Europeans and Italians didn't have their act together. The Chinese had their act together. They had like a ESO already. Like they had an actually funded observatory where people were working and like, I mean, government funding. That's where the thing is at. Summary: surviving companions. So essentially, like converging. Sorry, got sidetracked. Like the classic scenario for remnants in the Milky Way seems to be ruled out. So the really classic, so we've never found a really unusual star in any of these remnants. And I mean, also this scenario is like, at least for one remnant, it seems to be unlikely. And I mean, you can argue the simplest hypothesis that all 1As are the same, or at least all cosmological 1As are the same. Next scenario predictions. I love these flame transitions. They're a little bit slow on the Zoom thing. Flame propagation. So we have these two things, and I'm going to go to the two extremes. We have the 1.38 solar mass white dwarf, not 100 mass white dwarf, but 1.38 solar mass white dwarf. And if you burn this with a deflagration, you will make too little nickel-56 to explain the top 180 supernova brightness. If you burn it with a detonation, you will make too much nickel-56 to explain the supernova brightness. So for these objects, you need to have a deflagration followed by detonation. That happens on Earth in diesel engines, like the non-human diesel engines. This is exactly what this is.
You want to remind people what deflagration is?
Oh yeah, that's a very good point. So deflagration is a flame where you preheat the fuel. Like a candle, for example, like when the air moves up, like you're heating the fuel up before it sort of like reaches a flame point. And so that's subsonic burning. And detonation is supersonic burning. It means like you have this shockwave racing through, and you sort of like immediately shoot it up in density and burn it there. And so detonations make nucleosynthetically much more of this nucleostatistical equilibrium nickel-56. And yeah, you please do jump in if there's questions, but that was a good point. And we have a 1 solar mass white dwarf on the other hand, and the interesting thing is like it's unclear really how to ignite this. There are scenarios now, but there didn't used to be. This was a much clearer case. But if you take this thing and just detonate it, you get something that looks like a 1A. And so people were fascinated with this. This is like Seminar 2010 or so. So there's multiple people that have done this and said like, if you detonate a 1 solar mass white dwarf, it looks like a 1A. And so one of the differences between them, they make the same amount of nickel-56, otherwise they would have been ruled out as models. I mean, the stratification, oops. The stratification is different. So deflagration is very turbulent. And so like, mixes things through much more, and detonation is very stratified. So you should like, get like layers of things that are relatively clean from the burning process. And so you should be able to see this if you could reconstruct the supernova from observations. And this is exactly what we're trying to attempt. So this thing is called Supernova Tomography. One of the really, really cool things about supernovae is that essentially we can see the star from the inside. Like even as for seismology, we can't really see what the star is made of inside, or the exploded object. And so what we have here is we have the red area, which is sort of underneath it, which it's like optically thick, and we have the area above the red surface, which is optically thin. And so as the supernova expand, both of them expand, but in mass space, this sort of contracts in. This photosphere contracts in. And essentially we can then approximate this like, this is sort of a black body. It's not quite right, but I mean, let's assume this is a black body. And then what these lines here are is this features imprinted by elements in the envelope. This is a little bit more complex because you have these all P Cygni features and they're all blended together. But this is sort of a useful thing to think about. And that means, in theory, if you have a spectral time series, any spectral time series, and we sort of assume it's spherically symmetric and stuff like this, thing that we always assume, we can reconstruct the exploded star, which I think is super cool. But like for each one of the observations, you then have parameters. I mean, if you take like 10 elements for each one of these spectra, if you have 20 spectra, you have 200 parameters, which is difficult to do. And so for now, the status quo has been like, you essentially do chi-bi, you sort of like play with these and you find some sort of fit. I mean, obviously there's no uncertainties involved in this, there's no degeneracies like with these parameters. It's not really reproducible. And a solution might not be the best, especially if you're searching in 200-dimensional space. And it's very work intensive.
Sorry, I have a probably stupid question. Like in the beginning, you talked about models. One of them was like helium blowing up and shock waves. That doesn't seem very spherically symmetric.
Yes, I mean, so you have the helium racing around and then compressing the star, and then you have an ignition hotspot. It's a little bit off center, but it's near the center, and you essentially start from there. And so that is relatively symmetric. I mean, people have simulated it. It's relatively spherically symmetric. I mean, we also know observationally their type Ias are relatively spherically symmetric from polarization measurements, but also from remnants. They look very round. So we think it's a good approximation. I mean, probably not perfect, but a good approximation. Sorry, did this answer your question?
Yeah.
And so the dream is like, we essentially go and we like do this all in Bayesian statistics and do a full posterior over this 200-dimensional parameter space. So I mean, for some, this, I think for no one here, this is new, but I always put this slide in because not everyone is familiar with Bayesian statistics. Essentially, like, what we need a model which sort of takes this like, layer cake of a supernova and like evaluates it and makes a spectrum. And so we need some sort of comparison between spectra and between synthetic spectrum and observed spectrum. And we also can put in like, some priors and assumptions where we say like, oh, it doesn't make 2 solar masses of titanium because the star is only like 1 solar mass that exploded. But it's pretty difficult to do, and so like for a long time I thought maybe this is not possible. So even if you do this in a very simple case where you sort of just say like we just do 1 spectrum and you sample over 14 parameters, like 10 elements, and like like radius and temperature of the photosphere, like this becomes very, very big. And sort of to sample such a space will take, with one of the rate of transfer codes that we're using, TARDIS, 420 years. And so this does not seem to be possible. And this code is optimized for this kind of work. So this doesn't seem to be possible. So a couple of years ago, we sort of saw that there were starfish. Who made starfish? No, who made starfish? Ian Zicala. Ian Zicala, like, and other people had the idea of like, using machine learning to sort of like, emulate the spectral comparison. So what is this? So before I go into emulators, like, why don't we do the classical machine learning approach where we sort of have synthetic spectra, have a machine learning algorithm, and like, point to like, the individual abundances. And the reason why we don't do this, because in the synthetic spectra and the observed spectra are drawn from different populations. The observed spectra have dust in there and other things. And we, again, do not get posteriors out. We can now, with modern machine learning techniques, it's possible, but I mean, back then we didn't. So what we did is like, we made machine learning, we made an approximation to TARDIS, which is the code that we're using, which evaluates much, much faster than TARDIS, but essentially gives the same results. And this is what Dalek is. And I mean, essentially we have a speed up of, this is no longer true, Jack, right? 50K, I think it's now 10 to the 8 or something like this. And we produce a spectrum that essentially looks the same as TARDIS. So we made a fast TARDIS.
So why is it now so much higher than the?
Because I think I evaluated this wrong. I think like, Jack did it right.
Okay.
And I think like, I don't know.
I also do it on the GPU. I don't know if you originally trained on GPUs.
I did train it on the GPU. I don't know if we valued on the GPU. Anyways, I think like, I don't know. Either I did it wrong and probably Jack did also something better. And so now what we can do is you can put this emulator directly into the model. And so this is what like, Jack has been doing, which is probabilistic estimation of like one of these explosions. We still like, that's the TARDIS collaboration. For now, like we're not taking spectral time series, but we're taking like a single spectrum just to make it easy for now, to sort of like look at the outside of this supernova. And so we use 2002 BO, which is a well-known 1A, and it's well observed and also well studied, and has also been like spectroscopically fit manually by Steele et al. And other people. And it's an early phase where photospheric approximation holds, which is important for the random transfer code we use. So our model that we use is like TARDIS. TARDIS is a steady state Monte Carlo code. It has the photospheric approximation where you just like put this in and you say like there's a simple black body coming out. It has non-LT in various forms and like line interaction, electron scattering, and now continuum interaction as well. So like it's continuously growing. It's an open science code. And essentially, like, what it does, it takes one of these models and spits it out, and now we have the emulator on top of this. And so the prior is like, this is something where Jack did a lot of cleverness. He sort of went to like a model archive where people sort of had evaluated like many different explosions. The Heidelberg Supernova Model Archive dataset, which is an open dataset of explosion simulations. And essentially, he used the mergers, detonation, deflagration, and delayed detonation models to inform the prior, like how big. Like how much variation do we allow in the different parameters? We looked at all cells above 10,000 kilometers per second. This is a thing specifically for photospheric codes, and we're using a 60% quantile bounds. I mean, we can argue if this is useful or not. And we're treating the abundances in log space because that makes it easier from an astrophysics point of view. Anyways, these are the priors. I'm not going to go into them, but I mean, this is something questions should arise. And Jack is an expert. We're just including you in the questions there. So the other thing is like, the likelihood, like directly comparing the models to the data is really difficult because I mean, there's dust in there, and TARDIS has some physics issues like many codes. And so models are not perfect, and we're trying to make a likelihood function that sort of accounts for this. So we have intrinsic effects as well as extrinsic effects, and we sort of decided to compare not directly chi-squared, but I mean, to go into a different space. So we used a technique similar to SNIT, which sort of removes the continuum, and then we compared this so it would emphasize on the lines. And we scale the uncertainties to also capture systematics. And this was a lot of like, Jack's work did this, and so you can see like, we have the traditional spectrum, and then we have sort of like, the transformed spectrum, which I think was, and then we compared both observed as well as synthetic in that space. Sampling, we use the fast TARDIS, the Dalek emulator, the likelihood, as I said, and then like the priors came from the Hasmo models. And so what comes out is now this wonderful, and I don't expect you to read the labels, but this wonderful big space in 14 dimensions. And one of the cool things you can now do is you can sort of like go here and say like, this is a likely area, but I think what is much more interesting, you can say like, oh, this is an unlikely area. I think the unlikely areas are much more interesting than the likely areas. And you can rule certain models out. So this is one way to sort of like look at the fit, and you can see that the model, these are sort of the 95%. This is the green is the observed supernova spectrum. Then we have the black one is like the mean of the likelihood, and then we have the 95% quantiles and the 68% quantiles. And you can see like, now there's not a single fit, but I mean, it sort of has bands where you can see like what can it fit, or where does it try to sort of like adjust. And so these are 1D posteriors broken down. And this is, the black is our posterior. And we can see, for example, magnesium is not constrained. We can immediately see like, if you do this by chi by I, which I think this group is already convinced of this. If you do this chi by I, like it will mislead you. Then we have like a result that was previously fit by Steele et al. 2005, and they did this by hand. And we sort of used, they didn't have uncertainties, but they had like measurements over multiple spectra. So we just used ranges that they were finding. So these are the essentially like Steele et al. 2005 results. Then we have the deflagration. So we can compare we now can compare to theoretical models, and we have the detonations. And we can see, for example, for silicon up here, it does not agree with the deflagrations. So type 1A's, at least O2BO, is not a deflagration on the outside. And here we can again see like also, so this was silicon and this is sulfur. For both of them, like, it doesn't agree. I mean, for others, like, it's a little bit more, there's some agreement between deflagration and our posterior. But it's still like, I think mostly suggests that deflagrations for type 1As are ruled out. And I think this is a great thing to sort of show that this works. We do not expect type 1As to be deflagrations. So the summary.
Delayed detonation, right?
Sorry?
The delayed detonation.
So the delayed detonation is a deflagration on the inside and detonation on the outside. And so essentially what you would see on the outside is mostly detonation.
Mhm.
And so for the minus 10 days spectra, we can only sort of like, you cannot really tell. And this is what Jack is working on. We will have to go further in and like do more things. And in the newer fits, like, I think you now have it. So you also try to figure out what is the discriminant between deflagration and detonation. Okay, first full probabilistic reconstruction of a type 1A supernovae. So this was O'Brien et al. Last year, and we now can direct comparison between spectral time series and exposure models, which I think is the cool thing. We can now actually like take this and not say like, maybe there's a silicon line or how much of it, but we can actually say like, this is what the posterior is. And I mean, there's still a lot of work to do, but I think it really shows a way to more quantitative sort of ways of looking at transients. Type I, as I said, will mislead you, and I think this may be the wrong group to tell this to. I think everyone is sold on this. And the next step is many more supernovae, and also multi-zone models. This is a little bit more tricky because you have these 200-dimensional things and emulators to build for this. But I really also want to highlight the work of the emulators. I think like, the emulators, I think, are really a new hope for bridging theory and observations. And there's two more projects that I'm going to quickly highlight, specifically one by Andrew Fullard first, who's my postdoc, well, not any longer after June 1st, he just got a position as a research software engineer. And essentially, like, you can use polarimetry to do mass estimates of massive stars. I mean, I'm not going to go into this. But what we could do is we could then, like, do, like, posteriors of mass estimates. And so this is the mass of the star that we found, and this is, like, the probability. And these are measurements that were done before. And you can see other methods find these different peaks that we find in our posterior. And that means, like, if you do these maximum likelihood estimates, you will find an answer, but it's not the whole story. You might just be wrong. I mean, maybe you find this peak, but it's this peak. And so I think this is a really nice way of, like, we can really now bridge observation and theory. This is a different wave transfer code specifically for polarimetry.
So this is the same, this is the same star with a factor of 10 difference in mass?
Yeah.
Very quick.
Yeah.
Yeah,
So-
but it's
so-
Wolf racer. Okay, that's it. It's like a Wolf racer with a lot of mass.
The
So you don't know where
the difficult to, I mean,
the photosphere is.
but there's still some of the, we have also smaller, we have also like better constraint. But I wanted to show this because this is multimodal, and that the two multiple methods show you different modes of this. And so if you don't do the full thing, you will just see one of them. And so this is essentially, the Wolf-Rayet star has like a spherical wind, and you sort of like, when you see this at an angle, you have polarization signatures that tell you about essentially break the sin I degeneracy for the mass estimation. So you measure, really what you measure is sin I. And this is like, our very own Mark's paper, and specifically working on stripped core-collapse supernovae, and doing sort of similar things that Jack are doing, and also developing the emulator. You can see, like, again here we have these wonderful, like, correlations in parameter space, correlations and uncertainties, which I think is, I mean, this is very preliminary work, and this is, we're still working on this. I think really shows that emulators, I really like emulators. I think they're a very nice way of bridging this. Okay, so maybe at least part of this is maybe no, in the sense that, like, we don't have deflagrations of these massive white dwarfs. But I think, like, this is where we are at with the flame front, and so we're now doing many more supernovae and multi-zone modeling, as I said. The last discriminant is an interesting one. So one of the things, as I said before, like, the same number of nickel 56 is produced in all models that are still alive today, because ultimately, if we didn't, then they would have been ruled out. But one of the differences is, at the very core of the explosion, you have either more neutralizations or less neutralization. And that means you have either less nickel-57 and cobalt-55, or you have more nickel-57 and cobalt-55. So why does this matter? It doesn't matter for like the first couple of 100 days, because like nickel-56 decays in a couple of days and cobalt-56 in like 77 days. But essentially, like after a long while, like I think after 600 or 800 days, you start getting the decay of cobalt-57 and iron-55 starts to matter compared to the cobalt-56 decay. So if you observe a supernova very late, you could potentially measure the central density of the exploded white dwarf. And so, like this Rob Goodall have done this and have sort of said, like, if you just look at the bolometric light curve, and bolometric means like not funny bolometric, but actual bolometric, 0 to infinite wavelengths, you would sort of see a difference here. And so luckily,
you would see a difference if you made, like, if you had an accretion model, right? This is a merger. Okay.
This is an accretion, but I mean, ultimately, it is the central density of the white dwarf that exploded. So I mean, we cannot say anything about accretion or merger. I mean, we can sort of circumstantially infer, but if we can measure this difference and can say which one it is, I think like that would help us. So this brings us to 2011 FE. Like it was one of the closest supernova, well, until 2014, one of the closest supernova in a lifetime. Essentially, it was very close, and so we have exquisite observations. And so it gave us a chance to sort of follow this up. Normally, you can follow up supernova until a couple of 100 days, and then they're just way too faint to observe, to test this experiment. And so what we did is like, we started with Gemini photometry, then there was a couple of spectra by Stefan Taumberger and Melissa Graham, I think. There were 2 spectra in 1,000 days. And so like then we had 2 programs like doing HST multicolor photometry. And it even goes further now. I mean, I think Chappie went to 2,000 to really get HST multicolor photometry and then reconstruct these bolometric luminosity. And that's the problem. Like we don't really capture 0 to infinite wavelengths, but we capture only part of this process. And I think that was one of the issues. And so essentially, like we got this, like these are the beautiful HST data points. And so Chappie et al. Said conclusions merger, and Dimitriadis et al. Said a conclusion accretor. And so clearly, like they must disagree on something. And what they disagreed on is like the physics at these late stages essentially is in physics in perfect vacuum. We are orders of magnitude beyond the vacuum that you can produce on Earth. So effects like freeze out and several other things start to matter. And so depending on like how you essentially model this, you get different outcomes. So one of the things at these very, very late stages is like all your only energy carriers from the radioactive decay are electrons. And so if there's no magnetic fields, they essentially fly out, and the mean free path length is longer than the remnant. So most of them do not interact. So if you include magnetic fields or not, doesn't matter. The observed window is maybe 20% of the total energy. I mean, this was estimated by Franzen and Björkstrand. And so the recommendation as an additional energy source also was sort of suggested by Franzen and Björkstrand, where they sort of said, like, if you put in energy now, you ionize something, and then, for the atom to find and recombine, that might take 2 weeks, and that changes the slope that is so important for measuring these. And so what we did is in 2017, I sort of tried out different models, and I said, you can't tell. Like if you just multiply exponentials together, you can't tell. And so I think what you really need to do is you need to go in and you need to model time-dependent NLT physics precisely. And so I have this crazy idea that we can do this and then use emulators to infer the central density. And potentially what it will be that the central density, the emulator central density that we will get will be so large, the uncertainties that we can't tell. But I think it's still worth a shot. We can get the density pre-explosion, which I think is pretty cool. So one of the problems is the current TARDIS code is we have this photospheric approximation and it works well until 20 days after explosion. But as I said, this is again Mars space, this goes away. So we have to add additional physics to TARDIS, which essentially is Andrew Fuller's job. And as I said, TARDIS approximates the energy using the inner boundary, and so we need to remove the photospheric approximations. We have added gamma ray deposition. This is what Andrew we're currently working on. Add non-thermal effects. And I mean, this is something that we're hopefully working on, and we're hopefully being able to make distinct measurements of the nucleosynthesis, which then gives us density estimates again.
Sorry, can you say a few sentences about the non-thermal effects?
Sorry?
What are non-thermal?
So non-thermal effects means that, I mean, only part of your energy goes into the thermal electron pool. I mean, you have essentially in the decay, you make a lot of, through Compton scattering and other effects, you make a lot of fast electrons. And so you need to take this into account. You can't just use normal Boltzmann-Solvers anymore. So as I said, I think light curves are powerful probes into the inner explosion physics. They're visible for a long, long time, for more than 1500 days, and potentially there's magnetic trapping involved. Extreme reverberation effects with these data we can rule out, but I mean, you still need to take them into account to make this precise density measurement. And I think there's more detailed modeling being added to TARDIS, which is the radiative transfer code that we're working with. Okay, this brings me to the conclusions. I think this accretion scenario, this where you go close to the Chandra-Sekhar mass and explode out of multiple reasons, is unlikely to be the major component of type 1a supernova. I mean, it might happen, but I don't think it makes the majority of them. Out of the reasons that I mentioned, and there's much more research into this than I'm giving credit for. There's accretion, you see X-rays in elliptical galaxies, for example. There's not enough X-rays from these accreting systems, and there's many arguments that sort of suggest this is not the right way. This accretion, the squish scenario, where you accrete helium and sort of burn it and squish the white dwarfs, unclear. I mean, at least what Josh found might not happen, but it's still a pretty promising scenario. So maybe the secondary somehow explodes, and there's a new paper out by Rudiger Packmore that sort of explores this. And so maybe it is the other scenario, but then the question is, what prediction does it make, and how do we rule this out? I think the type 1a puzzle has multiple things. As I said, surviving companions is one of them. Late observations plus nucleosynthesis I'm particularly excited about, because you could actually get to the physics of the center of the star. I mean, supernova tomography, I think, as we've shown, and as Jack shown, is that we're at the start of this, but now that we sort of have the machinery gone, we can really do this for many 1As and see how different are they. And I think that's where I'm going to end my talk. And there's many more. Oh, it doesn't show up there. There's many more that I haven't mentioned here. And I'm going to thank you for the attention. And there's more if you want to know more about natural language processing in our papers, but you can ask questions about this. Thank you. And is there questions from the audience? You got some questions.
So can I ask you a question about your likelihood functions and your emulators?
I'm gonna direct to Jack.
I actually want to direct to both of you. Are you guys using the same likelihood estimators across the different subtypes of models? For the different subtypes of supernova, right? Do you have emulators for stripped envelope supernova? You have emulators for 1As? Are you using the same likelihood function estimators for the emulators across them?
Oh, that's a good question for both of these.
Yeah.
I'm actually not sure, because I don't know what your likelihood function is.
Yeah, I would say yes and no. I mean, we're effectively doing very similar things. I know we both remove the continuum, for example. I mean, the details of how we actually do that will probably be slightly different. But yeah, I mean, basically, I think we're doing the same processing.
Do you find a big difference? Have you found a big difference as you change the relative ways that you're removing the continuum or modeling them?
As far as different ways of moving continuum, I mean, I've only tried it with removing it using basically the method SNP, which is actually code written by Mark in Python, versus not, and it does improve the fits. I also play around with actually infer uncertainty parameter additionally, and that actually helps the posterior converge a little bit faster when it estimates its own uncertainty. And I think that's also just That's the only parameter I've noticed that really affects the rates of convergence and where you get in models is how you characterize the uncertainty.
So I played around with different methods for removing the continuum, for example. And as long as you pick one method and are consistent in using that method for removing the continuum from the synthetic spectra and the same method for removing the continuum from the observed data, it doesn't really have that big of an effect on the posteriors that you get. But of course, the different methods for removing the continuum actually does make kind of a large difference in terms of what the flattened spectra look like.
Right.
I mean, there's not really a great way of choosing the best method.
No, that's why I was curious, because that in itself is a very hard problem, is how you compare those spectra.
So I think, yeah, and ultimately we have to do this because like we're making this photospheric assumption for TARDIS, which I think like we overestimate the continuum specifically in the red. But the idea is that we, in the end, don't do this. In the end, I think the dream is that we're modeling like 2D spectra on the chip, but I think that's a little bit further away. But in between, we could sort of think about like adding adding dust and things like this in, as long as we have the physics in TARDIS correct for also doing the doing the photospheric assumption correctly. That's correct. But yeah.
So people here might be interested in cosmology and implications. So given that we're still kind of hunting for the progenitor and the explosion kind of details, what are your suggestions for if we want to continue using Type Ia for cosmology for precision measurements?
I think there was a really nice paper by Adam Rees a couple of years back that sort of like explored like what are the different uncertainties, and I think like the progenitor question is one of them, but it's not the major one. I mean, for us, from a cosmology point of view, we're more going. This is more on the nucleosynthesis side that we're thinking about. On the cosmology side, we're more thinking about type 2p supernovae. So type 2p supernovae, like in theory, relatively easily standardizable if you sort of like think about like you have this entire hydrogen envelope, and for a long time it stays on this plateau, and you can sort of estimate you can measure the velocity of the photosphere. And you know when the supernova exploded, and so you can get the radius. So if you have a radius and temperature, you have a distance. And so this is something that we're really investigating. I think like specifically for near field cosmology and measuring like the expansion rate in the near field universe. I think like that's the reason why we're going. But Type Ia supernova, I think it does matter, and I think like we can. Once we can model these things much more precisely, we can then also turn this into much more precise estimates for luminosity. So I think we are still one step before that, where we're really just trying to figure out what they are. And I think like once we know what they are, we can then go into like what are the assumptions that will be wrong, in the sense that like what are the assumptions that we made wrong in the past that we can then like add correction factors to.
But what if you just say, well, since we have all these uncertainties, let's just go with one kind of supernova, Type Ia supernova, because you showed like there's a huge range, 2 order of magnitudes, factor of whatever 6 in luminosity. So would you say just especially kind of in the next era of LSST with lots of data?
I think one of the problems is you're talking about there is like what if the supernova in the earlier universe are different than the supernova is in the current universe, and I think like this is one of the problems that we can then identify. And so I don't know how strongly we can definitively say like this is one kind of explosion versus this is another type of explosion purely from photometry, but hopefully from follow-up we can sort of model this. But I think this is also where Deck's work is going, and where we're sort of trying to figure out like out of all the 1A spectra, like how different are they? Are there many different are there subtypes within sort of the cosmology?
So, one possible conclusion of this is that the 1A progenitors are double white dwarfs.
Yes.
What will be the observation that fully nails that? Because right now it's kind of the absence of, your argument is the absence of evidence, and I like the argument. There should be remnants, we don't see them.
Yeah.
So will that be resolved? Does Lisa find these, or does something?
Yeah, Lisa will find these. I mean, we know there's double white dwarf systems. The question is, like, just because there are accreting white dwarfs from main sequence stars, and I think that was for a long time that drove the story. Like, we see these systems, we see these explosions. Obviously, one must go to the other.
Yeah.
But as we see, this is a dangerous line of argument. So I think Lisa will have the same problem. Like we see these things, and so the rates for double degenerate, I think, are in the binary population synthesis and the observations are closely approaching the rates of the type 1As. This sort of single accretion scenario, that rate is not quite up there. We would have to have different mechanisms to make enough. But what we are really trying to do is not necessarily answering like, I know this is the flashy thing to do, this is the progenitor, but we are saying like, what is the central density and what is the flame propagation? Which I think is a much more, I like this because it's very physical, it's a very clear like measurement. And then like once we have these numbers, we can then say like what scenarios is this incompatible with? Rather than specifically saying like, oh, we want to see if it's double degenerate.
Good. But is there an observation? Will there be an observation at some point that nails it? Or is it always going to be in a situation where you have some?
I think, if you have a spiraling event.
I agree with by the way, I agree with the philosophy that you should focus on things you can measure.
Yeah.
I totally agree with that.
Yeah.
I'm just
So
saying that.
if it's pure spiraling,
Yeah.
the question is what you mean by nails. If I could tell you that the central density, like if I could tell you the mass was a solar mass white dwarf, it would still not, or if I could tell you like what exploded was a solar mass white dwarf, it would still not tell you how it got there.
Yeah. Or maybe you could see that it had very high specific angular momentum.
You can argue from the point of view. That's I don't know. I don't know if you're the judge. I wonder if you'll allow my evidence. I would say like white dwarfs peak at 0.6 solar masses.
Yeah.
So you somehow need to make this, but then you could say, well, you just make it differently than an inspire. But I don't know what other scenario there would be how to make it. It's 1 in 100 white dwarfs need to explode as a 1A supernova for now.
The horizon out to which, if you can think of there's a horizon out to which Lisa will give us a good census of white dwarf binaries, and there's a horizon into which we will see type 1A explosions.
And so I think Lisa doesn't go further than our Milky Way.
Far, yeah.
And so I think it's 300.
We have to get a type 1A in the local group then.
It's I would say yeah.
Although we could at least identify where they're likely to go off in the local group. So hundreds of thousands of years from now, astronomers will be like, oh, it was that. Binary that Lisa found.
It's one every 300 years in the Milky Way, and I think Lisa doesn't go much further than Milky Way in terms of detecting white dwarf spirals. But
even 1 in 300 years is a little aspirational in the sense that nothing seems to have gone off in a while.
That's why I drink red wine. I try to be healthy, and I sometimes run. Anyways, so I think that's, I'm not that worried. We can use circumstantial evidence to do this. In galaxy evolution, many of these things are much more circumstantial.
For sure.
And I think we need to be much more fine as stellar physicists in the future to do these things and sort of say statistically this is the most likely answer.
At some level, eventually you can imagine a world in which you can only set up the initial conditions for the explosion this way, and we will accept that argument, I think.
So if you made a perfect if you from ab initio and run this, and that's the only thing that fits.
Yeah, and you can imagine that it works well, and
then the question is this bijective? Can you go from the end results, or is there a distribution that's too large?
But still,
No,
I'm good. But it's frustrating though.
Maybe it gives us a challenge. If it was easy like
needed. More data and more funding and more theory.
Yeah, always more funding.
I think Mark was right though, the way he introduced you. I think it was correct.
What did you say?
For failing to find the
That's right.
failing to find it.
Trying to fail.
It turns out to be an important result.
Even for collapse.
Trying not to fail.
Collapse. If you didn't find Cassay's.
That's right. Yeah, I also
So
did.
it's for all supernovas.
That's right, yeah. No, I know.
You guys are always joking and says if you don't want to find anything, you should get Wolfgang on the project.
but it is true that one of the things about this kind of time domain astronomy is you can't, you really, there is truly no going back.
No.
You know, if we knew where the supernovae were gonna go off, we would do super deep
Yeah.
observations now.
LC will be exciting, then we can see the, potentially catch them early and like,
Yes, early is so important. Yeah, obviously we make very big clues by being early.
any other questions?
Okay, thank Wolfgang.
Well, you have different times go up. I mean, nobody says that all have to be the same.
No, I know, that's the thing. It
So I
could be
think
a
that's
diversity, yeah.
So